superconductivity. Welcome.
Dzień dobry. For those who do not know the lingua franca of the place, so then good late morning, okay? Let's see if it works. Oh, it does. So, I would like to say a few words about the strongly correlated systems. I use the term correlations, even strong correlations, but in a completely different sense that Professor Bennett did. But actually I could use also the term entanglement, and what is amazing and differs from the Professor Bennett's talk is that if you have quantum phase transitions in infinite systems, the entanglement appears back again, although I don't have a very good quantitative model for it. So it's not like that two are working very well, but three, they are already not entangled, but there is some, from three to infinity, there is a long way, as we see. Okay, so plan of my work is as follows. Very probably I will say just a few words about limits and about Fermi-liquid concept of quasi-particles due to Landau. Then I will show the border for the Fermi-liquid, or the Landau Fermi-liquid, as we say, is the localization transition, which is sometimes is known under the name Mott and Hubbard transition. And then I will say actually a few words about also the Mott and Hubbard type physics in quark-gluon plasma, and I won't talk about from lattice of cold atoms to superfluid. And then I will say beyond the localization threshold, what are the strongly correlated systems. I won't talk today, to disappointment of some people, about high temperature superconductors, which is my specialty, but I will say a few words about the non-Landau Fermi-liquids and about quantum phase transitions. And then what else? There are some very interesting physical, experimentally observable facts in those systems, strongly correlated condensed matter, namely that the effective mass may depend on the spin direction. And this very, very concept may have far-reaching consequences for the quantum theory, even in the non-relativistic case. I won't talk about this fractionalization of charge in the condensed matter, but as I said above, I will say a few words about quantum phase transition. So we start with this person here. So, somewhat I would probably should go there because I would like to see the things. As you know, this is the theory of Fermi-liquids. He created the term Fermi-liquid. It's really Landau Fermi-liquid. Fermi had nothing to do with it. Actually, Fermi was not alive then. And then there was the second part, which is vibration of the Fermi-liquid. As you can see, we have 60th anniversary of this creation of this phenomenological theory due to Landau. One of my graduate students said, oh, it's 60 years old, so this theory should retire soon. Well, not quite, okay? So, what we have? What we have with Landau is the following thing. I won't show any formulas, but what we have with Landau is as follows. What he says, essentially in the very first sentence, that we have that this Fermi-liquid is, it is assumed from the beginning that the energy of the excitation is a functional of the distribution function. In other words, the distribution function, in this case statistical distribution function of Fermi, Dirac, or Bose-Einstein-like, is the fundamental quantity. Essentially, Landau, throughout his life, if you look at his curriculum, he essentially was obsessed with going beyond the concept of Hamiltonian and Lagrangian. So that's why he created order parameter and directly constructed thermodynamic macroscopic quantity such as free energy or Landau free energy. He created this two-fluid thermodynamics of Fermi, of Bose superfluid, and then Ginzburg-Landau theory of superconductivity based on the notion of macroscopic wave function, which does not obey Schrödinger equation, but obeys instead a nonlinear equation, which is called Ginzburg-Landau type of equation, and so on. And this was the other thing. So he said that the energy of the interacting system is a functional of the distribution function. And therefore, and then said, oh, in today's language we would say, so it's density-density interaction, so you have kinetic energy of this, let's say, Fermi gas, of electrons, of helium-3 atoms, and then you add interaction with some phenomenological function, and times density, because it's an interaction. And he says that this interaction takes place, it was a very brave assumption, takes place only, strictly speaking, on the Fermi surface. Because, of course, near the Fermi surface, this is the place where the particles will scatter due to interaction, because in order to be able to scatter, you have to have field state, but also empty states to which the scattered particles go into. So therefore, what is deeply inside the Fermi surface, this maximal occupied state in the fermion gas, doesn't matter. What matters is just near the Fermi surface. And that was a very brave assumption. And it's amazing how this thing works as almost everything what Landau did. So then what he got from this phenomenological scattering function, he said this is just at Fermi level. So it depends only on angles between the momenta of scattered particle, which means that this function can be divided, can be expressed through the Legendre coefficients, and with few coefficients of the composition of this function, you can describe all the experiments. And that's what he did, and what he did get. He gets that immediately that the mass is renormalized, but he was actually very happy that the mass renormalization is finite. He knew that it's 1 or 2 free electron or free atom, free fermion masses. Of course, if the system is magnetic, this enhancement factor is rather 5, 10 rather than 2. And then we have Fermi energy. So this is still from the gas, this quantity survives as the maximally occupied state in the Fermi gas. And if you use just Fermi type gas type of concept, it's something like that with fermion momentum. It's something like 5 electron volts. So he says, so it's better to talk something like that. It's 50,000 Kelvin or maximum 100 Kelvin. But of course, he already put here, because he said the interaction mass is not a good quantity in quantum mechanics, so it must be renormalized. No, so this, due to this renormalization, this quantity may get reduced by factor of 5, so it's from 50,000, it gets something to 10,000, but still, it's quite big quantity. And then, of course, particle density, we have a condensed system, bulk system, we have something like Avogadro number of particles, so it's huge, and this leads to few things, that this maximally occupied state, those quasi-particles have classical velocity, which is called Fermi velocity, something like 5,000, 8,000 kilometers per second. So you have a piece of cosmos already in the non-relativistic system, because you have a cosmic velocities appearing here within these very, very tiny light particles. And then, of course, since you have at the level of 5 electron volts, you have 10 to 22 states. So then immediately you see that within 1 electron volt and you have something like 10 to 22 states. So therefore, for all practical purposes, this is a continuous distribution. Of course, mathematically you may say if Riemann integral is well defined and so on, but let's forget about that. Physicists forget about that, and you can say even if you work on the scale of microkelvins, this is still practically continuous distribution. So therefore, for all practical purposes, we have a continuous distribution of the particles, at least in this big system. And then you calculate the Broglie wavelength, add the Fermi energy, and you are getting that it's something like 1 inverse Ångström size. So therefore, lattice constant is 2 Ångström. So therefore, those matter waves overlap very strongly, and that's why the system is coherent, even though it's not interacting, because those matter waves form, even though the particles exclude each other, but they strongly interfere with each other on this scale. And then Coulomb interaction, of course, now Landau said that's Coulomb interaction, at least expectation value, because we are working on the phenomenological semi-macro state, is something like volt or less. So here I have something like 5,000 Kelvin, here I have something 5,000 Kelvin, here I have starting something like 50,000 Kelvin. So probably that's why this picture that we have only interaction at the Fermi level is probably correct qualitatively, but it turns out it's quantitative. And then he makes a big, big jump. And this is absolutely ingenious. If you look, that Fermi-Dirac distribution derived for the gas, this gas holds on. And of course, he coded it in this mapping, this adiabatic switching of interaction, but it amounts, down to earth, it amounts to the fact, assuming that Fermi-Dirac distribution goes without change. Is it going without change? So then let's test it. So this was 57, and then 87. Of course, people started testing it, Fermi and Bose-liquid theory, on helium atoms. And the beauty, and already this was said, but even Fritz London earlier, that helium-3, for helium-3 and helium-4, electronic shells are the same. So the atoms speak to each other on macros, practically the same. But they differ in the small nuclei, which are 6 or 7 orders of magnitude smaller. Here are 3 nucleons, here are 4. So whatever you do, this will be boson, this will be fermion. And this small nucleus dictates how the atoms behave. This is the true quantum mechanics, quantum statistics. But even though it's hidden, it's immersed in this Fermi sea of electrons, it dictates how the system behaves on the macro scale. So let's take helium-3 and try to test the Landau concept. So then, in 1985, comes the beautiful experiment of Mook, and this is directly measured by neutron scattering of the Fermi-Dirac distribution, and helium-3 sucks like mad neutrons. So therefore, the experiment must be very subtle, because helium-3 wants to be helium-4, and so on. And you can see the beautifully works Fermi-Dirac distribution. This is experiment at 1 Kelvin or less. And then he fits Fermi-Dirac distribution function, but it turns out that the Fermi energy, which is in Fermi-Dirac distribution, is not as the Fermi energy value what would be for the gas of the same density, but the Fermi-Dirac Fermi temperature is 3 times smaller, or 6 times smaller. So therefore, so what does that mean? That we have still Fermi-Dirac distribution for these liquid or interacting particles, fermions, but with the renormalized characteristic. And then a year later, Dennis Greywall has measured linear specific heat, which from the Sommerfeld time, we know it's directly proportional to the mass. And then as a function of pressure in this liquid helium-3, you can see that at ambient pressure, you have something like effective mass enhancement with respect to the free atom value, something like 3, and it goes to something like 6, and then bingo, at third something atmospheres, Fermi-liquid gets crushed and crystallizes into a solid. So therefore, this border represents a natural border of the Fermi-liquid concept. But you say, that's nothing strange. There is a first order transition to the solid helium, and that's it. But then you could ask, of course, here are fermions. So could we understand whether this is as just two different sides of the same story? And that's essentially the Mott localization of whole atoms that spontaneously they arrange into a lattice, and that's the phase transition in the thermodynamic sense, which you can of course show. And now we can see, can we incorporate within Landau picture at least this thing? And then this is just an illustration. Years later, with my former student Adam Richards, we have calculated exactly the distribution function for nanorings, let's say of hydrogen atoms. These are exact results, and you can see this is distance between hydrogen atoms with respect to the Bohr radius. So here hydrogen atoms touch each other because the lattice constant is 2. And you can see that the distribution function is practically Fermi-like distribution at t equals 0. Then there is discontinuity, and then there are some tails. But you can see this discontinuity, which is called the Fermi ridge. Now, not just discontinuity to 0 as in the gas, because the particles interact. So therefore, some of the particles, dense particles, can get pushed off to the higher energy states. And then as you increase the lattice constant, which means the interatomic distance in the ring, then it slowly smears out. There is probability of finding particle in given momentum state is 1/2. So therefore, you have as many holes, empty states here, if it's 1/2, as many electrons you have here. So it gets smeared out. Yeah, but if it gets smeared out in the reciprocal space, in the momentum space, this means that the system gets localized in the real space. And that's another sign of this localization, since here is the finite system, so therefore it's continuous, it's a crossover phenomenon. But you can see that it's not only here, even nanoscale you see that, and also you can see a degree of universality of the Fermi-Dirac function. What is this localization? What is this Mott localization? If you go back to the Drude formula, so even 50 years back, at the beginning of the 20th century, you have the formula, classical formula for resistivity, and you know that it's proportional to the mass of the carriers, and in the denominator there is concentration of carriers times their lifetime, their scattering time. And now you can say, if this state of this Fermi gas with finite resistivity, or zero resistivity even, if it gets destabilized, which means it goes to the rho equal to infinity, so either the mass goes to infinity, or the carriers get freezed out, or the scattering gets so strong that you have distraction, dynamic distraction, and here you have, in a way, you could say static distraction by the system itself. And this, customarily, this is called Mott-Hubbard transition, and this one is called Anderson transition. How can you see that easily? Then you can use still, and this we have done. I have worked with a group at Purdue University and then University of Chicago by Tom Rosenbaum and George Honig, and then Tom Rosenbaum measured Hall effect, the classical Hall effect at low temperatures, and the specific heat at the same time. So Hall effect at given current and given field is proportional to the carrier of concentration. So if you have Mott transition, linear specific heat which proportional to will diverge, but the Hall constant will stay constant. So it is beautifully confirmed. This was 20 years ago, that it's this rather this than that if you have a Mott-Hubbard transition. So therefore the picture is like that. The momentum which we are talking about is a translation momentum through the system, which is not conserved, strictly speaking, because you have a motion in a discrete lattice. There is some degree of symmetry. It's a discrete symmetry, but not full symmetry with respect to the momentum, to the displacement, and therefore you have either atoms, the electrons localized on atoms. So let's say these are modeled by hydrogen atoms, so they have spins. So immediately the system gets rid of spin degeneracy and orders into beautiful anti-ferromagnetic pattern. Or suddenly when you squeeze these things, the system bingo, and the skeleton of ions remains, but the gas collectivizes. And this is one of the most violent phase transitions. For example, resistivity in vanadium sesqui oxide, such a compound, the resistivity changes in the 1 Kelvin range by something like 8 orders or 10 orders of magnitude. So it's really a violent transition between those two. So in school we learn about quantum mechanics, in solid-state physics we learn about that. And I was actually, since I graduated in particle physics, I was really amazed that in one textbook you have that, and the other you have only that. And of course, then my professor said, young boy, the Professor Neville Mott has solved it long time ago, but it turned out it was not so completely. In the other language, you may say, if you go from the not atomic side, but from electron Fermi gas or Fermi-liquid side, you may say that you have well-defined Fermi surface, Fermi topology of Fermi surface, not necessarily like that sphere. And then if the mass goes to infinity, since kinetic energy is proportional to 1 over m, so therefore it should reduce to that. But that violates uncertainty principle, because you have momentum very well defined, the system has to be localized. So uncertainty of position is finite. So this is not good. It rather transforms at certain points, either continuous manner, it disappears, or in most frequently in discontinuous manner into a lattice of spins, and here its atomic type Heisenberg uncertainty relation is fulfilled for the atomic states. Okay? What is this localization? And that's the original Sir Neville Mott derivation. When I was a postdoc at Imperial College, Sir Neville talked to me, Józef, this is just back of envelope, my derivation of the Mott criterion for the transition, transition. It took me quite few years. Only when I started writing the book on condensed matter physics, then I realized how Mott, it was really trivial, but it took only 10 years me to understand. And the essence of the argument of the about localization is as follows: that we have average kinetic energy per particle. It's something like half of Fermi energy. If highest is Fermi energy, average energy is half of Fermi energy. Okay, this free half is because the density of states is not just a constant. And then you can put here from the gas, and you can see that this energy is proportional to the density of particles. In the power to 2/3, at least in 3 dimensions. And then let's try to estimate Coulomb interaction classically. Of course, if we are at the border of insulator, then dielectric constant is well defined. So therefore, the classical energy per pair is something E squared over the average distance between electrons, but since we calculate everything per particle, so there is additional 1/2. And then you have, but this is the distance between electrons. If every atom contributes with 1 electron, so it's volume divided by number of particles to 1 over dimension of the system, in 3 dimensions is 1/3. And then you can see the role in most clear way. You can say naturally, if my kinetic energy, which is coming from real exemplification of uncertainty principle in a solid, is equal to the average energy of interaction, something must happen. Either gas must get destabilized, or vice versa. Since Coulomb interaction, when dominates, it wants to spread those electrons as far as possible, which means on parent atoms, because every atom contributes with 1 electron. So it goes to the gas. And surprise, surprise, if you compare those 2 quantities, suddenly such thing appears, which is, even though I have only electron mass and Coulomb interaction, which is the Bohr radius, effective Bohr radius, for the medium in which you have mass m star, and the Coulomb interaction is screened epsilon times by the screening. And this times density at this point, this is a universal number, something. So the effective Bohr radius appears even though there is no Coulomb attraction here. The Coulomb attraction is only with this effective mass or repulsion. And this is a universal number. So there is something. At lower densities, interaction dominates. At high densities, kinetic energy dominates. And this is a kind of asymptotic freedom that kinetic energy interaction is larger and larger when you squeeze the sample. But the kinetic energy grows even larger, and therefore the ratio gets diminished with the increase of density. Of course, now it's not so simple because the system is atomic. There is periodic lattice. So therefore comes, soon after Hubbard, comes another guy. Everybody thought that Landau is diffing, but Hubbard is not diffing. But what he said is essentially, you have to start from atoms. So therefore, your classical Coulomb interaction in the proper particle language, which means in second quantization, is if you have kinetic energy as you had before. Here you have statistical distribution if it's expectation value. But then if the particles are almost atoms, so they overlap only a little. So therefore, they see effectively this quantum Coulomb interaction of this classical long-range interaction only when the states overlap. And this is this U, Hubbard U, where the particle practically overlap when they are with opposite spin on the same atom. And of course, then, since this is interaction, since you have just one orbital per atom, so therefore, if they interact on the same atom, they must have opposite spins because of the Pauli principle. So therefore, you have to start from something like that. And now, what Hubbard said, actually his first paper was a failure. I talked to him and he said it was absolutely failure. Fortunately, a year later, he has written another paper. And he said, what will happen if this short-range interaction in this atomic language will exceed this kinetic energy? If this term is larger, of course, it's diminished by this probability of having two particles on the same time, which gets diminished by the increasing U. But what happens if, anyway, if they are of the same? So in other words, what he wants to say, I have the spread of single particle energies. In solid, it's finite. It's not electron gas. They are bands. And the bandwidth, the characteristic energy, is related to these hopping integrals. It's number of neighbors times the... So this is something like 1 electron volt, 1 volt. And then, of course, there is... The interaction depends how many particles you have. What is the density? And then, of course, what is the magnitude of the interaction? So therefore, the universal, if any universal behavior is divided by the relative scale, relative strength of those two quantities by the filling, and so on. And then you calculate. What do you get? In the simplest case, of course, now you have no perturbation expansion, not just interacting electrons on the Fermi level, because here, this acts in real space. This is in reciprocal space energy. So therefore, if you transform it to the K space, the scattering will be all over for all electrons. There will be really boiling soup, not just something ripples on the surface, as in Landau theory. So what do you get? You get getting with now you cannot use, you have to use variational approach. Here, name of Martin Gutzwiller comes in the simplest case, but also some other people, like Kanamori and of course Hubbard, but Hubbard in different ways. And you see that effective mass now is mass of electron. Here is denominator U over UC. That's critical value of interaction I will define in a moment. So therefore, if U goes to UC, this is essentially Fermi energy, this UC, if this, twice the Fermi energy. So therefore, you can see that the effective mass divergent. So you may have effective masses 1,000, and these are observed, and they are called in condensed matter physics heavy fermion systems. Then you have kinetic energy. And here, let's use again, when you have now renormalization of this mass. So therefore, if mass gets increased by the factor by 2 or 3 orders of magnitude, so kinetic energy, this Fermi energy, which was 50,000 Kelvin, now it gets reduced by these correlations to this something like 50 Kelvin. So you have really, you really have quantum scale for the classical interaction kinetic energy like that. Then the total energy gets reduced, and if you reach this, reaches this critical value, it gets reduced to 0. So what does it mean? That there's interaction which wants to spread the electrons as far away as, and kinetic energy which wants to make them dense, because to make the Fermi energy kinetic as lower as possible. So therefore they compete very strongly, because one is repulsive, one is attractive, because it's so-called band energy, so it's not just classical positive energy. And if they are equal, they kill each other, so and reduce to 0. Then Pauli susceptibility. You have Pauli 27 work that you have here directly density of states, but here is again this factor appears, and there is another factor appears, and this is the so-called Stoner criterion, that if this gets 0, so therefore system spontaneously goes into ferromagnetic phase. But you can see that really you can have at t equals 0, you have immediate, you are in trouble. Because instead of having Pauli susceptibility, you have to go, you have infinite quantities, you have singularities. So therefore, you have a quantum phase transition at t equals 0. So what we teach students, that as temperature goes to 0, And then we have quantum mechanics. This quantum mechanics, this quantum mechanics is singular. It has singularities of physically observable quantities. And that's why there are all these quantum phase transition, quantum critical phenomena are so interesting in condensed matter physics. And the difference with other disciplines is such that here we can measure most of the things. I would say even experimentalists are ingenious in this respect. And here there are some very good experimentals who do that. For example, our chairman, Andrzej Ślebarski, Darek Kaczorowski, and I could see even some other people, experimentalists, who do that. Maybe not in such simple form, but that's what they observe. And then linear specific heat, since this is proportional to effective mass. So this linear specific heat is not just ripple, small amount of electron at low temperature at kT, since the whole energy states and the Fermi energy gets squeezed in. So small kT thermally excites almost whole system, and that's why it becomes very, very big. And then, of course, resistivity becomes the magnitude of spin. Beautifully, you can observe that it goes from what you observe for electron gas expectation value to the atomic value spin 1/2 rotating in the atomic state. So indirectly, we see that really those electrons acquire full spin value 1/2 expectation value as they start sitting on the atoms in the localization threshold. And this critical value is of the order of 8 times kinetic energy, which is, I would say, what I said is just something like 2 times Fermi energy. And of course, what I said already, that this is after this 60, 90 years of quantum mechanics, we see that we have a breakdown, not the breakdown that they are wrong. We have to complement them with something different, that the picture that in the interaction comes not in perturbative way, they leads to singularities and quantum critical phenomena. And then this is the phase diagram for the system with localization, which I have this is one of my first papers. It's already 30 years ago. It's 87 paper. And you can have here temperature, and here you have this value of U over this critical value of. And what we observed then is that you can have transition from Fermi-liquid to localized fermion, but then as you hit the sample, it goes back again, re-entered metallic behavior. And then there was a school of theoretical physics in Zakopane. I think this was Helmut Stacz from Bielefeld who comes and shows these diagrams for hadronic matter, temperature. Here we have constant number of particles. There, since everything boils really wildly because it's high energy physics, so therefore in their case chemical potential is constant, but still here you have constant number of particles, here you have constant chemical potential. Still they observe a similar thing, you can translate each other, with this critical point. And in condensed matter physics, this critical point, I have predicted in 87, it has been only, as beautiful paper in Science, it has been checked experimentally in 2003. I don't know about quark gluon plasma. And then here there is another critical point, at t equals 0, which is quantum critical point. Of course, here they do not have critical points because they included also the locked color flavor locked superconducting phase. If we include magnetism or superconductivity, there is another phase appearing, and therefore this is a hidden critical point. So maybe this is the same thing. So how you could understand this in this language? And that's the next page. Let's take relativistic fermions. This is this hasn't been published anywhere. It's just for the purpose of students and so on. So suppose we have Dirac relation, suppose we have just particles, and of course we assume that we have system of massless quarks, just to make the argument transparent. So we have something like that. For that, those particles, ultra-relativistic particles, I can calculate Fermi energy, and it turns out before it was raw to 2/3, here is to 1/3, and then of course you can say, and I said, okay, they have confinement. So they have some sort of reference energy. And here I put something that is something like harmonic type of confinement. K is greater than 0. Here probably in this effective repulsive potential between quarks, there is some gluon matter is probably somewhere contained. And of course, it can be linear or quadratic, doesn't matter whether this confined potential is linear or quadratic. The argument remains the same. So I have pair something like that. Pair quark, I have something like that. And then again, what I do that I compare, when I compare those two energies, and what I'm getting is that there is a critical concentration in which the hadrons, the quarks confined in hadrons, they decompose into quark Fermi-liquid. And how is it? And effectively, it's like that you have this correlation energy ρ2 minus 2/3. In our case before, it was 1/3. Then I have kinetic energy to 1/3. And therefore, there is a transition at high density to what I call, it's my version, Professor Hoft probably will object that I can call it asymptotic freedom, but it's a poor condensed matter physicist version of the asymptotic freedom, okay? And you have this thing. And why, even though this helped me to understand why this confined potential, even though it can be infinite, what the system gets deconfined, because this average distance at which it works, this condensate of the quark, is essentially in limited region of the distances. So therefore, those tails, infinite tails, are not seen even in the condensed state. And then there is something what is how it looks like in condensed matter state, such a how many? Oh, it's already 0, so I will be finishing. Okay. May I take 2 minutes or 3 minutes? Is it okay? 5 minutes. Ah, it's 10 minutes. Okay. Chicho. Okay. Well, essentially what I wanted to show, because as you know, this year in January, metallization of hydrogen has been achieved for the first time. So molecular hydrogen was squeezed by Isaac Silvera and his postdoc at Harvard. There is huge discussion and going on whether they really observe the metallic phase. But this is 500 gigapascals, strictly speaking, 495. This is something like 5 million of atmospheres. So really very big, very, very large pressures. Why this is interesting, this hydrogen? Because there are guys who are saying that if hydrogen gets metallized, it immediately becomes superconducting, high temperature, room temperature superconductor. And actually we have recently published a big paper in PhysRev and estimated, it's not published there, metallization is there, but if we estimate transition temperature, unfortunately with the Macmillan formula or anything like that, going beyond BCS, we get 800 Kelvin, whereas the Dubai temperature is something like 500 Kelvin. So certainly something is not good with our calculations, but it's true that people from Częstochowa, from Radosław Szczęśniak group, they are getting also very big, very large values of superconducting transition temperature. If this was discovered, it would be wonderful. And that's why this hydrogen in this localization, delocalization from molecular stage to atomic metallic state is so interesting. And the last thing is about quantum phase, not this one, that what is quantum phase transition in the strict sense? What are those singularities? But we have system on indistinguishable quantum particles. We have Tc equals 0, which means no thermal entropy, so no, like in classical critical phenomena, the energy fights with entropy. Here the energies fight with each other and almost compensate each other. So very small entropy or disorder move the system, they are like tongue of the balance, move the system either in this phase or this phase, and this is the critical point. And then you have singularities, for example, like that, or like that for specific heat at constant pressure. And of course, we must know the quantum statistical temperature for T greater than 0 because we are approaching limit of T equals 0. And that's this entropy which defines this critical regime as you go with T going to 0. And this is really a very, very big, there is large interest, very widespread interest in that point. For example, between magnetic metal, conventional metal, between heavy fermion, conventional metal, superconductor, normal metal, localized, delocalized, and so on. Okay, so these are this type of, I will not talk about my beloved subject of spin-dependent masses, but I will tell you what is the fundamental issue there. Suppose normally, we have effective mass and spin quantum number as internal quantum number. And therefore, the particles are indistinguishable. Because in the non-relativistic sense, what distinguishes the particles is the mass. What distinguishes, of course, apart from charge, what distinguishes proton from electron is that they have vastly different masses. But now, and so therefore you can symmetrize the spin wave function, because even though they have different masses, electron and proton, we have this spin singlet or triplet states, because spins, from the spin point of view, they are indistinguishable. But if you have mass dependent on direction of spin, then the spin is stuck to the mass. So therefore, the particle with spin up carries different mass with spin down, and therefore they become distinguishable. So the question is, can you have quantum mechanical particles which go from this state to this state, from indistinguishable to distinguishable? And that's what we are working on. But of course, I have no time. So therefore, I will just move to the conclusion. So the hierarchies. If the interaction is U less than 0, we have superconductivity. And the difference between attractive and repulsive interaction in solids, in any, that if you have very weak attractive interaction, the particle condenses immediately. If you have repulsive interaction, like Coulomb interaction between electrons, therefore there is wide range before any localization model takes place. And that's where the Landau Fermi-liquid theory fits in. So therefore, we have electron gas, then we go to Landau Fermi-liquid until we reach the Stoner criterion, the system becomes metallic, and then we reach the Mott system, and from that, this is the world of strongly correlated systems, and you can see, name it, magnetic semiconductor, heavy fermions, neutron stars, quark-gluon plasma, and so on. So this is the second, so about this you probably have heard, about this you have heard, but the physics of today is essentially going on, at least in condensed matter physics, it goes, very much is going on in that area. Thank you very much, and sorry for.